Welcome to the ADS Workbench tutorial series. My name is George Fan. I'm the CEO of Aerodynamic Solutions. In this session, we'll be focused on configuring a 2D single-row steady simulation. Here's the process we'll go through to set up the run. First, we'll need to create an aerogeometry file definition. This involves specifying the 2D airfoil geometry, initializing the flow field, defining the aerodynamic conditions at the inlet and exit, and setting the computational boundaries. Once we've completed the aerogeometry file, we'll specify the mesh settings for code WAND and the flow solver settings for code LEO. Now to set up the case, you'll need to have a text file that defines the airfoil geometry with a known number of points and a known input format. For this session, we're going to use a sample case that's included with the Workbench. It's called VKI-Vane2D. It's a vane. It's specified by 81 points in an X1, Y1, Y2 format. And the geometry data is located in a text file called rawgeometry81.txt. Let's get started. To begin the process, we'll take advantage of one of the 4 integrated wizards provided with the Workbench, the 2D wizard. The 2D wizard is located in the File menu under New. The first thing the wizard will do is prompt you for information about the name of your case and the project which you wish to associate it. We'll name the case VKI Vane 2D, and then we'll associate it to the project called Test Project. Step 1 for creating the aerogeometry file is to define the airfoil geometry. This includes naming it. Here we've named it VKI Vane 2D. Specifying the unit of measure, English or metric, we've specified English, and pointing it to the file that contains the aerogeometry data. In our situation, it's located in a text file called rawgeometry81. The wizard will then peek into that file to determine the number of points defining the airfoil, and then ask you to specify the input format that was used for the geometry. There are a couple choices in the 2D wizard: X1, Y1, Y2, XY constant radius, and X1, Y1, X2, Y2. In our situation, it's X1, Y1, Y2. The next step is to define the blade gap. This can be determined by knowing the span-wise location of the airfoil and the number of blades in the row. For n blades at a radius of r, the blade gap is 2 pi r, the circumference, divided by n, the number of blades. For this example, we'll use a blade gap of 2.2638, which corresponds to 20 blades in the row at a radius of just a little over 7 inches. You can also use this section to make some adjustments to your geometry. If you haven't fully defined your leading and trailing edges, you can have the wizard enhance one or both for you. Most people have already fully specified it, so they'll just take the default, which is assume closed trailing edge. You can also rotate your airfoil. The airfoil will pivot at the point 0, 0. Finally, if your airfoil design system always generates geometries pressure side up or pressure side down, you can use this option to flip the airfoil along the x-axis without having to regenerate the geometry data. Once you've completed the airfoil geometry definition, we'll move on to flow field initialization. By and large, we recommend taking defaults, which is for standard air with 0 translational speed and free stream turbulence levels and length scales that are typical of rotating machinery. Nonetheless, you can use this section to make adjustments to the default values. For example, if you want to enter translational speed, you can enter it here into the translational speed. If you want to enter gamma for something other than air, you can enter it here. If you or your aerodynamicist has experimental data that provides more insight onto the actual turbulence levels and length scales, you can provide that information here. And then if you are going to be operating in something other than air, like oxygen, helium, or nitrogen, you can change the molecular weight of the gas here. In our situation, we're operating in standard air, so we're going to take the defaults and move on to step 3, which is defining the aerodynamic conditions at the inlet and the exit. For this case here, we're going to provide the information at the inlet as follows. The Mach number will be 0.15. The total pressure will be 25.4251. total temperature will be 751.14, and there will be no tangential flow angle. If you do have one, you have two ways of specifying that flow angle, either axially or in meridional fashion. In addition, we'll specify the static pressure of the exit plane, which in our case is 15.44. Once we finish the aerodynamic conditions, we'll move on to the computational boundaries. For 2D simulations, boundaries will be defined as a percentage of the axial chord length. So let's take a moment to walk through the diagram. So for an airfoil of axial chord length bx, what you'll need to do is you'll need to specify the upstream boundary as a percentage of bx, the downstream boundary as a percentage of bx, the trailing edge span as a percentage of bx, and the height ratio to give you the ratio of height at the inlet over the exit. In our situation here, we're going to specify an upstream boundary of minus 50%, which means that we'll take the upstream boundary, and set it at half the axial chord distance to the left of 0. We'll also specify a downstream boundary of 165%, which will bring us 0.65 of an axial chord length to the right of the trailing edge. We're going to treat the trailing edge span at 100, so it's the same as the axial chord length, and we're going to specify a height ratio of 1, which means that the height at the inlet is the same as the height at the exit.